third. Right. Yes. Yes. Okay. Okay. If you are available on the April of 23rd, I think we would like to invite you to the demo to do a demo of your project one. Okay, we can discuss this after class. So today we will be talking about visual transformer.
我哋係 KB 嘅，佢係唔知幾多 GB 嚟嘅。
佢嘅輸出係 per net per second of KB 不可嘅愛，
有1000倍嘅。
所以我冇咯，絕對冇。
Okay, so let me just download this PowerPoint. Sorry for the delay. Okay, so today we will talk about the VLM, Visual Language Model, and Vision Language Model. So we will start off with recapping last week and also give you some background. So last week we talked about decoder-only transformer, which is a GPT-2 architecture. And we used autoregressive to generate text, and we discussed about how sampling strategies work, such as temperature, top K, and nucleus. And we fine-tuned the LoRa for text model for text summarization. So I know some of you cannot run Lab 3. I think it is because I have changed the authorized level of the server. So I think there is a folder that I need to authorize you all to have access for the Hugging Face to download, to load the folder to load the model into the folder. So I've asked you to think about the effects of when you increase the corpus size, what will happen to the tokenizer, or what will happen to the tokenized per word. So essentially, the tokenizer works by splitting individual characters into multiple, we say, tokens in the first step, and then we try to merge the each token and find a new one. So we can formulate the number of merges. So if you really think about the number of merges is actually equals to the vocabulary that you defined minus the initial vocabulary size. So initially, you start with all, say, 256 characters, and then for each merge, merge A and T, which increase the vocabulary size by 1. And the question that I'm asking is about the expectant token per word. So it's the average token per word. Weighted by the word frequency. You can think of the expectations of the function, that is tokens per word. It's just a fancy way of saying the average. So the average tokens per word, written in some mathematical formulas. So the token count function, it will return the number of tokens that a word is split into after the BPE tokenizer. So you can see if the word is cat and the tokenizer split into 2 tokens, the function T of W will be equals to 2. And for if the tokenizer do not split the word D, it will just be the token function. The token count function will just output 1. So the expectations of the token function, which means taking the weighted average of all the token function across all the words, where common words like D contribute more than the rare words like some mathematical terms, which was trained during fine-tuning last week. So you can think of, because the corpus controls the actual frequency, because this sentence actually states take the weighted average. So the corpus actually controls the weighting of each word. So the weighted average, you can thinking of the frequency determining by the corpus size multiplied by the token count functions, and divided by the frequency of the word. So why we want to introduce this mathematical formula, it is only because we want to connect the average token function with the related with the corpus. So after this, we can imagine with the largest corpus size, we will have a better estimate of the true frequency of the word. So imagine a corpus where the appears 100 times, and tokenizer tokenized the word the is 1, and cat appears 10 times, and the tokenizer tokenized the cat into 2 separate tokens. And this one appeared 2 times because it's a very specialized medical terms. Does not appears normally in daily conversations. And it appeared, and the tokenizer split the word into 3. So the unweighted average would be treat all words equally, which is not what we're trying to measure. We want to have a tokenizer that actually tokenize the corpus in the most efficient way. So you want the to be a single token rather than this one to be a single token. And taking the weighted average would be weighting to be more important, and we will have the calculation of around 1 point something token per word. So the weighted average is much lower because the which is shorter and more common dominates the average. So as I have mentioned, weighted average reflects the actual tokenization cost when processing real documents. Okay, because you can think of simply because you do not want common words to be not in to be have more tokenized counts per word than less frequent word. Okay. So now we can rewrite the weighted average in a more useful form. And so you can think of after tokenization, so before merges, initially we have the token count of say 3, so equals to the number of characters. And the initial fertility would be F0, which C is the average characters per word. And the tokenizer actually saves tokens is the whole purpose of the tokenizer. So each merges combine 2 tokens into one, saving the 1 token each time the merge pair appears. So we can formulate the total token saved across corpus is S, and we can compute the actual ratio. So the token saved over the actual characters is the power. We can kind of measure the power of the tokenizer. So this represents the fraction of characters got compressed way by merging. So if a corpus has, say, 1,000 characters in total, after merges we save S, for example, 350 tokens, and then we can say, sorry, this is sigma. Sigma have the power of compression around 35 compression percent. So the question remains how the corpus size affect the compression rate. So does the sigma changes depends on how much training data we have. Of course, yes, because when you have a small corpus, you have a very bad estimation of the true frequency of the word. So imagine the true frequency of, in English, say TH, the true frequency is around 3.5%. With a small corpus, you might get something different. So this refers to unlucky because you underestimate the true frequency. When you underestimate the true frequency, you cannot effectively tokenize the corpus. And for overestimate, it's actually still problematic because you might underestimate other words. So with large corpus, the percentage will be very close to the true compression. And this is just some simple statistics that you might want to know, but you do not need to remember. So when you flip a coin n times, the observed frequency has an error proportionate to the 1 over the square root of n. This is fundamental results from the probability of central theorem. So actually this root is derived from some statistics. If you heard of variance, because variance often equals, there is a standard deviation squared, which is called variance. And because they computed, if you're rearranging the terms, you will get this funny little square root, but you do not need to worry about this much here. You just need to know kind of the relationship between the corpus size and the square root of n is typically the typical error. So you can look deep into the central limit theorem. It's essentially saying the corpus size is the sampling size of the actual text. So you can imagine this size is the sample size, and when you sample infinitely over and over across the population, the relationship is the square root of L with respect to the error. Okay. So the compression ratio, this is the perfect compression ratio you can achieve with infinite data. So this is assuming your corpus size is almost infinitely large, or I can put it another way, it's too large, it's almost like nearly the same size as the population, so you get a very accurate estimate of the actual frequency. And this is the corpus size. So if your corpus size is small, according to this equation, what will happen is you have a worse compression ratio. Okay, so what it most? Okay. Okay. It's because of the soup. I think the presentation is stuck. Okay, I think I might have to restart the computer. what happened today. Sorry for the technical difficulties. Okay. So for details, you can kind of find the relationship between the token per words against the corpus size. So at some point, it is not very useful to increase the corpus size, as you can see. But and each fertility is different from different languages. So there is diminished returns according to the paper that I have posted. This paper it suggests around 250 gigabytes of data for English to get an optimal tokenizer. So more than that, you will not get any better tokenizations. Okay, so another questions that I want to go through from last week is about question 40. So I asked you about is there any other metrics besides word count when you're comparing the AI generated text with the reference text. So there is a score called Rogue score, which calculates the overlap with references, which is I think a better indicator of the quality of the text generated. So if you are working on a data set that have these kind of reference sets, I recommend you to introduce the Rook scores into the evaluations. So Rook L measures the similarity using the longest common sequence. So the longest common sequence of word appears in the same order in both the reference text and also the text generated by your model. And the core idea is to find the longest chains of words appear in both order tags. So just a quick example. So if the reference, like the ideal case, for you to generate a sentence is something like the quick brown fox jumps over the lazy dog, and your model generate quick fox jumps the dog, and it will kind of convert this into count. This is the longest common sequence as 5 words. So it gives you a more kind of understanding of how the model performs. So there is another metric that commonly used is called bilingual evaluation. If you are doing translation task, you might want to introduce this scores into your project. So any questions? So I think I will skip the recap of self-attention multi-head today because it's all in the slides. So these are just matrix multiplications that I think you should be very familiar by now. So essentially it's just calculating the attention matrices using Q, K, and V. And you can go through this at home. But in here, I want to ask which 2 matrices contribute to the attention matrix and the reason behind choosing the 2 matrices. Anyone know which 2 matrices contributes to the attention matrix? So there are 3 matrices, Q, K, and V. So which 2 matrices contribute to the attention mechanism? V and Q? No? V and K? Q and K? Okay, good. So you now know the attention mechanism. Does anyone know why? Okay. No one? Okay. If you read into the mechanism of how QKV are computed, they are kind of arbitrary, right? Actually, the way that differentiate, we use Q and K to compute the attention matrix is because sometimes Q is refers to the target. So the source and the target for Q and K. So you will learn about this in the cross attention mechanism today. So let's start today lesson on how do we tokenize image. So today we will be talking about how to combine the image and text together and generate a useful multimodal large language model. So there are some fundamental differences between text and images. So images are, you can thought of it like continuous pixel values between 0 and 255. So no natural vocabularies. Unlike text, you can actually tokenize the text. But image, you might find it quite strange to tokenize. So how can you tokenize an image? So can you use the pixel values directly? It would be still problematic because the input dimension is considered quite high, and each pixel are treated independently. So with this representation, no spatial relationship will be captured. The computational is almost impossible. I think maybe someday it's possible with so much computation, but for this, for now, it's kind of computationally impossible. So what we want is actually a meaningful groups of pixels to preserve the spatial relationships and with a manageable sequence length. So there are three solutions. One is use a convolutional neural network, and we extracted features from the CNN. So the approach is to pre-train a CNN extract features. So this is this method is used by early VLMs. And today we will be talking about VIT, Visual Transformer patches. So essentially splitting the image into patches and kind of used by modern VLMs. And there is also the third method that we will be talking about in the next lesson, which is the VQ variation or auto-encoder code. Essentially, it's a discrete code book for transforming the image into tokens. So to define a visual language model is essentially a neural network that understands both images and text. So you is expecting it will read an image and you will ask it the questions and it will kind of answer some questions based on the image. So say, what is the color in the cat in this photo? It should output orange. It should be able to read text from images. So like you can upload an image to say ChatGPT and it will answer what's in the image. So in the very early stage of this development, a paper called An Image is Worth 16 times 60 worth transformer for image recognition at scale. So what it does is step one, converting image to patches. So when you have an image of say 224 by 224 image, you divide it into 14 by 14 grids. So chop it like a grid, and then so it patches will take up 16 by 16 patches. So there are in total 196 patches. And for each patch, it will have 768 values. And then we will flatten all the patches into a 1D sequences. Because of the slides, I will just use a 4x4 to demonstrate how they actually flatten the patches. So imagine you have a 4x4, you do it like 1, 2, 3, 4, 5, 6, 7, 8. So start off with first row, second row, and then concatenating all rows. So the results will be 1, 2, 3, 4, 5, 6, 7, 8. So can you think of any problem with this flattening? So what information has been lost if you just pass through this into a transformer? Yes, spatial relationship. Because if you read into the attention mechanism, it do not have any spatial information. So it treats the sentence as any order. So we need to add back the positional encoding. Okay. Yes, we need to add back the positional encoding of the visual transformer into these patches. And so here's the code of the image patch code. And then after we have the image patch, we will be projecting all the patches into a smaller dimension. So I think all of you now are very familiar with this matrix dimension multiplication. We have 160 196 patches, each with 768 dimension, and then we will do a linear projection, project into a space, an embedding space of 512. So with this matrix, you can project into 512. Okay. So I've mentioned all this, document processing, describe images, search products by images, and analyze medical images with explanations. Okay. So divide image into patches, flattening each patch and linear projections. And then we have to add the positional embeddings, and then feed the projection with the positional embeddings into the transformer encoder, and we have an image becomes a sequence of tokens. Okay, so about the patch size, you can pick different patch size, but according to the paper, 16 by 16 is the best one. So you can divide the image into smaller patch size, but each patch will have larger, so it will have larger pixels within, and you can divide into more patch size, but each patch will have smaller pixels within. So the paper actually suggests 16 by 16 is the good patch size. So you can run the code with the script. So in here, we will try to divide this image into patch. I actually already ran the code, so I can just show you what the code, what the results are. So when you run the code, you will get an image in the server, and here is a 16 by 16 patch looks like, and here is a 30 by 32 patches looks like, and this is 8 by 8. So the best one is 16 by 16. Okay, so here are the code. So the important part of extracting patches is essentially two functions. So when you divide, when you get the shape of the image as height width, you need to divide the patches, and you need to reshape it according to this function. So you can read into the documentation of the reshaping, and the reshaping function is actually a bit tricky to get used to because of all the dimensions. You have like 3 numbers to play around with, h divided by patch size, and so on and so on. Okay, so now we are going to talk about the entire visual language model architecture. So we have talked about how to convert image into tokens, and this is the first part, and then we still need to connect the vision to language. Some use cross attention, some use clip, other use sequence to sequence attention. And we also need to generate the text back. So today we will quickly talk about all these methods. So, but first we have to kind of familiarize with ourselves how language models see the image. So we need to connect the image to text, right? And we need to, after this, we need to decode back into a kind of sentence. So the complete pipeline is seeing it, conditioning with our image, and saying it back what the image is or what it contains. So these are the visual language model families. We have Git-based, Polygamma, which can be put into our server. But for Qwen2 visual language, it might be too big. And these are some open source models that you can try. But for our server, I think it is okay to train Git-based Gamma with 3 billion of parameters, around 8 gigabytes. You can kind of fine-tune with 4-bit precisions. Qwen is actually and also other options. But in the lab 3, we will be using Git-based. So Git-based is developed by Microsoft and is pre-trained on the visual and questions dataset. It's around 1.1 million questions. So here are the data sets. And this is the original Git-based paper. So you can see it's doing quite well for such a small model, say a landmark. It can kind of can read the image and read what the image is about. So when you look at this one, you can see it actually performed not too bad. Right? Order of Chinese food called Ma'apo Doufu. So it's pretty good, right? For such a small model. So the architecture starts off with raw image input, and then the image encoder that we actually that we talked about, flattening the 2D image map, projecting into the embedding size. For the text part, it also takes in the text and begin with the beginning of sentence token. For the text tokenization and embedding, the text is tokenized and embedded into the D-dimension vectors. Also, the text have to add the positional encoding and later normalization for text and also positional encoding. So for combining the two information together, the Git-based use attention mask. So it uses a sequence-to-sequence style attention mask. Text tokens tend to only predict text tokens and all image tokens. So image tokens attend to each other, so it's bidirectional with visuals. So this differs for unidirectional mask, which allow full intra-images dependencies. The image features are concatenated with text embeddings to form a single input sequence to the decoder. So after the attention masking, this is actually concatenated with the text embeddings to form a single input sequence to decode. Okay. So this is the attention mask. And remember the self-attention mechanism. We have Q and K to form this attention mask, right? And in here it sort of select the image with image masking and image to text attention and text with zero mask with the image in here. And we have also text to text auto generation. Okay, so anyone understand why this is designed like this? So why do we have to add all the zeros in here? Okay, so let's go through cross attention in here, and after going through cross attention, you might understand why do we need all the zeros in here. So cross attention is essentially very similar to self attention. So cross attention in transformer, essentially we have Q is coming from the target and K is actually coming from the source. V is also coming from the source. So this is the case of translation. So if you are doing translation, you need to use the cross attention because the source of the language, you also need to kind of have a target. So the target is considered to be the decoder. So ask the queries. The source, you need to have the encoder sequence. So in here, should I put image in the target or text in the target? So in cross attention, you have, okay, so let me go back a slide. So the question now we are asking is combining the text and image, right? We have to have the two information blend together. So the previous self-attention mechanism does not, it will work with some modifications, but we are talking about sequence to sequence attention. So it kind of blending the two information together with image and text. The question starting off with why do we have all these zeros, right? Why don't we all attend them together? To answer this question, you have to first think about what cross attention is. So essentially, if you blend it together, it's kind of like a overall cross attention, right? So for cross attention, we have Q, K, and V. Q is being the target. So what should we put into the target? The text. So the text in here is like asking a question. Is there a cat in the image, right? The text is like a prompt. So should we put this text into the target or the source? So if you think we should put the target into the, we should put the text, we should put the text into the target. Please raise your hand. No. If you should put the image into the target, please raise your hand. No. Okay. Anyone know what I'm talking about? Okay. So we are picking. We need to blend two information, right? Image and text. You want the transformer to answer something about the image, correct? When you type into the chatbot, you're like, what's in this image, correct? So what would the transformer do? It have to somewhat read the image, right? And answer you with the text.
If you use the text to the target, it will only use text to guess what the picture is. But it will not to recognize the picture by the picture. 对对对。
So there are two. So the target should be text.
No. A picture.
The target.
Source.
Okay, so I want you to think about this, and I'm just going to keep talking what is cross attention. So cross attention essentially, you have the target and the source. Traditionally, this is for translation. This example is for translation, it's not for image. So traditionally, we have the target, 3 tokens being generated. So we want to translate French into English. So we have the source have 4 tokens with the French, and we want to generate English token. So this is what we want to do. And traditionally, we of course transform the target into Q, source, K, and V in the source. We put V into the source because what we have is the source, correct? Because at the end of the day, is the V get transformed. The K and Q used to generate the attention matrix, right? Anyone follow? So V is what we have. Therefore, it must be the source. Because during auto regression generation, we only have V. We do not have the target. We want to predict the target from the source, right? So V must be the source. The relationships only captures from Q and K, right? So, okay, so now we compute the, that's what I've mentioned, compute the attention using Q and K. And this is just reducing the attention score. And the target is row-wise normalized because we want to calculate the probability of contribution of each vector from the source. Okay, so we can see because from the source we have 4 French words, so that's why the columns are 4 and the outputs are 3, right? Okay. So now we will project our source using the attention matrix and get back the output. So this is this is multi-headed. This is single-headed. And now we are going to moving on to the image case. So the image case, there is a subtle difference. You need to introduce some special tokens called CLS tokens, which seem very similar to the beginning of sentence tokens, but for images. So you add this in the images. Okay. So these are just like beginning of sentence tokens, like special tokens we talk about in text. And we are going to project our, okay, so beginning of tokens, so beginning of the image, and then we add the patch. Okay, so now we do the projections. So projecting Q queries to the projecting the query with the Q matrix into the Q, or with the weighting of the Q to the Q. So in these examples, I used image as the K and V. You can argue why can't I swap this around? Like why can I not swap the text using the K and V? Essentially, I think you can do this. So the answer to the question is you can do it both ways. But most papers use this kind of settings. So they actually use the text as count as the query. So the question is the text, like what is the cat is the question, right? So traditionally, query stands for questions. So what is the cat will be introduced into the Q matrix, and then you do the attention with the image patch. So the image tokens will be transformed to K and B, and now you can have so it is asking where's the cat, and it will try to find the patches in K. So it will try to find the patches in K, and then you can project project into the following sequences. Okay, and then all these are the same. So cross attentions is a VIT vision transformer variance. So go back to our question. Why do we zero out all this part? So why do we zero out all these parts? So this is called sequence-to-sequence attention mask. So I will let you think about this question over the break. So I will give you, I think 15 minutes of break.